Okay. Okay. Uh, yeah. So let me share my screen. So thank you everyone for joining this. So as we are here, we are going to talk about the soft matter seminar series, and we are starting with Karen's gravity and granular materials. And but before we start, I wanted to give a little bit of background where it started from and why we are here and who we are. So roughly speaking, so this is our agenda. We'll just introduce uh, to BPS and soft matter or complex fluids program. Then we'll go through Karen's presentation, and then we'll go through like a open forum like discussion. So who we are? So we are from NASA Glenn Research Center. So we are part of BPS, Biological and Physical Sciences, at NASA's Science Mission Directorate. We are responsible for the soft matter research. When we say soft matter research, it can be broadly classified into two areas, which is granular media and active media. And under active media, we look at colloidal science and non-Newtonian fluids and rheology. Our mandate is to promote fundamental science in micro or reduced gravity, um, for example, lunar, Martian, and which can actually capture the taxpayer's interest and imagination. And so my name is Suman. I am the lead discipline scientist of soft matter at NASA Glenn Research Center. So I have my colleagues, John, Tyler, Kelly. We all work together on this call. So so what this is like a very rough overview of microgravity research listing. If you want, you can use this QR codes. I have already put the links for this in the chat, so please feel free to actually just go through them at your convenience. As you can see, we have a rich history of looking into soft matter, of doing soft matter research, and so we are just going to continue uh, in this pathway. So the question is why we are here. So last year, during August, we actually organized three mini workshops where almost 60 plus soft matter researchers participated, and we talked about how soft matter can be relevant for future of space science. And it was a very enthusiastic conversation that we had. It was a total of 6 hours of workshop, and people were very engaged. We received a lot of positive feedback, and so we decided to keep the community engaged through this seminar series. So the goal is to keep the soft matter community engaged. We want to create a knowledge exchange platform and generate awareness. Now, at the beginning of this year, I sent out a Google form to all of you, to whoever is interested. So we have a lot of interest. If somehow you have missed that, please feel free to email me, or you can directly fill out this form. There is a QR code here that you can scan now, or I'm going to put the link of this form in the chat also. So before we jump into the into today's seminar, so I would like to mention that we are actively looking for postdocs and interns. As of now, we had in last 1 year almost 6 interns that worked with us. They are graduate and undergraduate students. So if you have an interested candidate, please let us know. Please feel free to email me, and we can talk with that person and see how that aligns with our interests. Now, I would like to take this opportunity to announce the next seminar, which will be on April 3rd at noon time, Eastern Standard Time, 12 p.m. And our speakers will be Dr. Lawrence Wilson and Joe Bradley, and they are going to talk about high-speed optical imaging methods for soft matter science. I'm going to send an email with a calendar invite today or tomorrow with the details. Please look out for that, and I would really appreciate that if we can keep this conversation going. So now coming to today, our speaker today is Karen Daniels. She is a great friend of the program. She is a distinguished professor of physics at NC State University. She received her bachelor's in physics in Dartmouth College in 1994, taught in a school, and then she pursued PhD in physics at Cornell University. She received her doctorate in 2002, and after that, she moved to North Carolina to do her research. I have sent, I'm so in a single word, she is extremely accomplished. Her research in granular media is something that I personally really enjoy reading, and we have a lot of conversations about the future of granular media in space science. I really enjoy all the conversation and the honest feedbacks that I receive from Karen. So I felt like she is the best person to kick this off, and it's a great honor to have her here. So I would now hand over this to Karen. And before we go into this, so we want to keep it very informal, but I think it will be better, Karen. I think if the presentation, you give the presentation, people ask the question at the end to keep the flow going. Okay.
Yeah.
Okay. So I would say, like, if you have a question, please put it in the chat or raise hand, or so me and John, we will try to organize the questions, and or we just raise your hand, and at the end of it, we can go through it. I think the talk will be roughly about 45 to 50 minutes of that time, so we will have plenty of time to like talk and get your feedback or ask questions. So with that, I will hand it over to Karen. Thank you.
All right. Thanks so much. Let's see, I need to share screen here.
And one more thing, if you are not speaking, if you can mute your mic, I think that will be better with regard to not distracting people. So we'll really appreciate that. Thank you.
All right, so I'm so honored to have been invited to kick off what looks to be a very exciting set of talks coming forward. And I added a preliminary title to the start of this after I sent in my title, which was Grains in Space, which should be read, I think, in the Pigs in Space, the voice of the Muppets. And so what I'm going to talk to you today about is the left-hand side, which is the kinds of things I do in the lab, and what they might have to do with the right-hand side, which is the asteroid Bennu, and what they have to do with each other. And sort of a theme that I'll come back to the same slide at the end of the talk, but why should NASA be interested in physics research on granular materials is a very good question. And I'm going to talk about sort of 4 ways that I think it matters. And I'm an experimental physicist, and I think that we need a wide range of environments in which to do our granular physics experiments, and I'll talk about why that might help us discover new phenomena and develop better models of granular dynamics. So that's sort of the physics side of this, which is where I have the majority of my experience. But then also, if we can do those 2 things, right, it can provide 2 really important things to NASA, right, which are that, understanding, solar system formation and planetary geomorphology depends on knowledge of granular materials. And, if we're going to go out and explore our solar system, we need to do that safely, and we need to be able to do in situ resource utilization. And again, all of that depends very strongly on us having a good understanding of the substrate on which that is happening. Okay, so how did a laboratory physicist get here? And so I was inspired by an email exchange with Henry Shroop, who's on the call, to go back, and I actually found the slide that I used for my final presentation as an undergraduate in 1993, when I was involved in looking for near-Earth asteroids at Lowell Observatory. And I enjoyed my summer doing astronomy very much, but ultimately decided not to pursue graduate study in astronomy. And meanwhile, 2 decades passed, and I returned to thinking about grains in space. I became an experimental physicist, and I signed on to do a postdoc with the late Bob Barringer. And the topic is actually the title of this talk, which is Gravity and Granular Materials. And our aim was to design an experiment that would fly on the International Space Station and use the fact that there was low gravity there as an important knob in understanding granular materials. And although our experiments never made it to the space station and got flown, Bob did make it thanks to the efforts of Matthias Sperl at the DLR. He made it on an iPad up to the ISS. Okay. And from that project, I got thinking, you know, as an experimental physicist, there's a knob that we have access to, which is to control the degree of gravity, and it's an important parameter looking at phase transitions and things like that. Go forward another decade, and I was in a chance encounter with the astronomer Martin Elvis at the Aspen Center for Physics. They have a habit of pairing up.
Excuse me, Karen.
Yeah.
Just a quick question. We're still seeing your title slide. Have you been
Really?
advancing?
I'm
Yes.
advancing. Yeah.
Okay, there we go.
All right. So now but unfortunately now you're seeing
The one with the lunar rover.
Yeah. Okay. So let me see. This isn't. Sorry, I don't use Teams, and so apparently this is not how things work. Let me switch to presenting in a window and see if this works better. All right, so this is what how's this? Unfortunately, now it's going to show my toolbars too. Can you guys see my slides though?
No.
Now you can't see my slides. This is not good. All right. Let me open share tray again. And now you see my slides, but with my toolbar, right?
Looks like it, yes.
Okay, into the advance.
I did not yet. There it goes.
Okay, all right. All right, so these are the four things I'm going to talk about. This slide will come again at the end, so no great loss. And then I've been talking about how experimental physicists got here, and here's my pictures. All right. So I hadn't thought much about asteroids, you know, in 20 years. When my office mate at Aspen introduced me to Martin Elvis, who asked me if I knew about rebel pile asteroids, because they were a granular material that existed in the solar system. And I had never heard of them at that time. And I just thought it was remarkable that there's a pile of grains that under self-gravity, you know, just, you know, exists as its own stable entity in the solar system, and set about asking questions about what those were and what it would be like to land on one. And, as in The Little Prince, on an asteroid, what if that asteroid is so weak because it's only held together under its own gravity? What does that actually look like? And that took a while to actually figure out how I was going to get an entry into that. And so that came about when, with collaboration with Josh Caldwell and Addie Dove at UCF, to say what happens if we fly some parabolic flights where we probe simulated regolith and ask what happens if you did put the Little Prince on the surface of an asteroid. Would he fall in? And how would he fall in? And how does that depend on the size of the body and what that level of gravity is? And that brings me right back to being an experimental physicist, where what I do is control some knob and look at the effect on the material parameters. And nothing I'm going to talk about today would exist without all of the students and postdocs in my lab who have made all of this possible, and a special call out to Jonathan Colmer, who's the person right here, who you'll see a bunch of ways that he's contributed to this effort from the time when he began as a postdoc in my lab and on to work that he's doing now. All right, so we can't talk about granular materials without talking about the fact that everything we know about them comes essentially from an engineering context, right? So for millennia, humans have been engineering with granular materials all over the world. And we know how to build stable structures. I have the Great Mosque of Mali and the Taos Pueblo, New Mexico here. We know how to move pharaonic statues across sand by lubricating with oil. All of these things that we learned how to do, right, are in Earth gravity. Okay, and as you know, we began to make these more quantitative, and an early effort to do that was, the famous, Coulomb friction that we learn about in freshman physics, and everyone's drawn a picture like the one at the lower right, which says that there is some sort of angle of repose that comes about from ratio of normal and tangential forces. And just like a block sliding down a plane, you can think of a granular material like that, and this is why sand piles on Earth have these very, very triangular shapes with very consistent angles of repose. Okay, and this is a collective effect in the case of grains. There's billions and billions of sand grains here, right, and all of them are participating in something like this. Okay, and you'll see already that there's a G that appears here. Okay, and we'll come back to that in a minute. So with quantifying our understanding, then you say, all right, all of the different ways that grains exist, right? They vary in size, shape, friction coefficient, roughness. Here's some lunar regoliths. It's extremely rough. Their density, their stiffness, their adhesion, their liquid ridges. So, both their own properties and their interactions somehow collectively give rise to bulk properties that are what we need to do engineering. And how that averaging happens, how you get from the microscale to the macroscale, is at the heart of condensed matter physics, and making that connection has formed a large part of questions that I have asked, okay, and has very, very many open questions. And so if we have trouble doing that on Earth, it's even harder to do that where we have less experience. Okay, so these are really, really hard problems even on Earth, right? And so there are disasters all the time involving granular materials. So there's a silo at the left that's collapsing. It was full of grains of corn, and it collapsed. The one on the right is a location that I have studied. So the Mud Creek landslide that happened about 5 years ago. And this is just for scale, this is a road across here. Okay, this is south of Big Sur in California, along the California coast. Entire hillside slid into the ocean. And luckily no one was harmed, but there was incredible economic damage from it. And so, both of these on Earth are known to be problems that are both dangerous and expensive. And if we're going to do things, out, in the solar system, we can afford even less risk on this effect. So we have to ask, what changes when you go to lower gravity? And I'm going to put this picture back up again, which is that when you solve this freshman physics program, one of the things that cancels out when you get that, mu equals 10 theta is the gravities cancel out. And so, one might guess that in fact angles of repose don't change when you go to lower gravity situations. Okay, many, many other things do, however, you do need to worry about. Okay, so if we think about escape velocity, right? So if we are visiting a rubble pile asteroid, and these are 0.5 kilometer in diameter, that means that their gravity, is a millionth of what it is here on Earth, and that means that its escape velocity is about the speed of a feather falling on Earth. 10 centimeters, 15 centimeters a second. Okay, is how fast something needs to travel to leave the surface of that body, which is an extremely small number. Okay, so anything that you do to disturb material, it's not coming back. Okay, so when you visit it. It also means whatever processes occurred to make that are occurring under that situation. Okay, and then you ask about other speeds, right? So I'm going to start referring to some work of some physicists who've worked in this vein, not necessarily with the aim of studying gravity on granular materials, but relevant to it, right? So if you lower the gravity, you have less compacted grains. Okay, and in numerical simulations, people have been doing this for a long time. They don't put gravity in because it's a complicating factor. So many numerical simulations are done at 0 gravity. And what Vincenzo Vitelli and his group figured out was that if you have less compacted grains, there's a lower rigidity modulus, therefore the sound speed, which is your square root of modulus over density, as you go to 0 confining pressure, that speed goes to 0, which means essentially everything propagates as a shock. Okay, and so now you have two competing velocities. One is the escape velocity and one is the sound speed, right? And they might you expect, right? One might be higher or lower than the other under two different circumstances. So what does that mean for interacting with some very small planetary bodies? Another thing that changes is the importance of Brownian motion, and this is a movie taken by Carlos Ortiz, who was a PhD student in my lab a while back. These are colloids that were deposited against a surface under fluid flow and are now being allowed to sort of evaporate off the surface. Okay, and so colloids are small enough that Brownian motion matters. And on Earth, we ignore those effects. Grains are athermal because the statistical fluctuations due to temperature are 10 to the minus 12th what you'd need to rearrange things under gravitational potential energy. But if G goes to micro G, right, this is no longer going to be as true. Okay, so relevance of Brownian motion will change in lower gravity. Electric forces will become more important. On Earth, we don't worry about van der Waals and charging effects unless we're talking about very fine powders. So, under 10 microns, say. And once you're in even just the lower gravity of the moon, right? There can be electrostatically levitated dust. There can be adhesion from van der Waals forces. And this has been studied in the context of lunar dust and some really nice experiments that have been done on simulated regolith, right? That sort of say, how you have, what the charging is as a function of diameter, right? And how that influences the forces. And this phase space needs to get mapped out, right? And this needs low gravity in order to be able to do these experiments. Otherwise, gravitational effects dominate over electrostatic effects. And this has real effects for solar system dynamics. So these are the work of Paul Sanchez and his collaborators, who I've talked to a bunch about this. And one of the studies I really love of theirs is to basically look at the rotation of asteroids as a way to understand what the interactions between the grains must have been. So if you imagine spinning something, right, and actually, since the strength, the material properties you get, tensile strength of this turns out to be at 10 kilopascals, which is about a tomato, right? So imagine spinning a tomato, right? Under what spinning force does it come apart? Okay, have you exceeded the tensile strength of the tomato? And for an asteroid, you can actually get a surface disruption limit that tells you about what the forces, adhesive forces must have been. And so since we don't observe asteroids in this quadrant, we know there must be adhesive forces, presumably van der Waals holding them together. Okay, but again, we don't have experiments with small particles and low gravity to understand what actually those forces are. So this is, again, a small grains, experiment type of situation would improve this. Another thing that happens, and I've experienced on parabolic flights, and many of the experimental platforms will have this problem, that G-jitter gets in the way of doing experiments. And this is an experiment on Earth, and it's not G-jitter, but it is something that's involving jitter. So these are the PhD work of Carrie Nickel, and this is a bucket of glass spheres, and this red platform at the bottom of it was being oscillated very, very slightly when this said disk on versus disk off. So disk on means very small vibrations at the bottom. And I'll play it again, and what you see is that what had been a stable duck and weight situation becomes fluidized by those very small perturbations, and the weight sinks and the duck rises, right? So this is behaving like a fluid under something that's kind of analogous to G-jitter, but would be even more dominant of an effect, in a low gravity situation. This is on Earth, and you can already see it. We know that gravity changes shear flows. This is simulations done by Lou Kondich and Ole Baran, and this was actually, while I was a postdoc, this was the experiment we were hoping to fly on the ISS, and they were doing numerical simulations of it. And one of the things that they had seen was for a shared granular flow, if you change from zero gravity to Moon to Mars to Earth, if you look at the flow rate as a function of position within the cell, you see changes in the shape of that shear flow. Okay, and so that means that we don't know how to predict things will flow in this environment if we've never done those experiments. This is much more modern work taken up by Wolfgang Lossart's group. Actually the same geometry as the floating duck experiment I just showed you. You shear a bottom per part of a system, and these are numerical simulations. And then you look at how the shape of the shear band changes as you go, in this case, from 1/3 of Charon to Earth to something that's larger than the sun. So 0.01 gravity, and 100 gravity. And you can see dramatic changes in the shear profile. Okay, without going into the details of what these orange bands mean, they are a shear band, essentially the place where things are shearing, and those are moving their shape and their location depending on gravity. And we're only beginning to understand those effects. Okay, so all those different forces are interacting. We have very few experiments which predict and test how they're going to work, and so you have to ask what can go wrong. And I think a lot of people know the problems, they've heard about the problems with lunar dust during the Apollo missions, and I like this quote from Eugene Cernan, and just what a problem it was for them to deal with it. It stuck to things, it got into things and jammed things up, and it wouldn't come off, and that's a real problem for engineering a mission. Okay, we have seen that the Mars rover, essentially got stuck in sand pits, right? We don't have fantastic methods of driving on surfaces where we don't understand the grains and their interaction. We've had difficulty landing on solar system bodies, right? So Philae bounced a bunch of times and got lost and was eventually found. We are not certain, how far in an arm on the surface of Bennu is going to go, and this arm went in about 1 meter. So this is the little prince sinking in up to his neck if he tries to stand on this, right? And so our ability to forecast and then resolve these problems ahead of time is hampered by a lack of modeling and experiments that support these sorts of engineering decisions that need to get made. Okay, and of course, all of these missions have been successful to varying degrees, but it behaved unexpectedly, which is why it's labeled them difficulties. Right, and some of them can lead to disasters if they go too far. Okay, and one that I want to talk about, particularly in light of doing in situ resource utilization, is this is something that we do all the time. If we're buying, this is a film taken at the bulk bins at my neighborhood grocery store, and we all know that when you try to empty granular materials, they have a tendency to clog, and solution on Earth is to whack it and it starts flowing again. But we have to worry that due to our lack of understanding of how to handle materials in these environments, we may have trouble transferring materials from one place to another. We don't have known methods for doing that. Okay. So why is this so hard? Well, again, this is even on Earth, right? This is a picture from a graduate student Farnaz Fazlpour that she took in an annular shear apparatus, which ironically is the motor is recycled from my postdoc work. So this is the NASA motor that's behind this. But when you look at this picture of sheared grains, right, we know that they have dissipation from friction and collisions. These are not ideal spheres. What you're seeing here are where the forces are located in that material. I'll talk about that a bit more in a second. But there's no good separation of micro and macro scales. There's large temporal and spatial heterogeneities. And so writing down a continuum model of this is an extremely difficult thing. And these are just for circles. These are just for circular grains. It's even worse when you don't have, nice, well-behaved, well-modelable particles, right? Friction is weird, right? When you have a frictional interface, the direction that you applied shear sets the direction of the frictional force. And there's a lot of history dependence. And as I mentioned before, we have these sort of athermal situation where things aren't rearranging themselves under Brownian motion. They get very stuck. Okay, so modeling is a persistent challenge, and experiments on the Earth are working on finding ways around this. And so several of the experiments that I'm going to show you in the picture that I just showed you come from us using photoelastic or birefringent polymers as our grains. So these look nothing like lunar dust. They are circles. If you held them up and squished them, they'd feel like a pencil eraser, but they're clear. And they have a cool property. So this is just a general property of polymers, that if you expose them to stress and then illuminate them in polarized light, normally if there's no force on the particle, the light can't get both through a left and right circular polarizer, so the disks are black. This is like a dark, so they're dark. As you put stress on each particle, it rotates the polarization of light by some amount, and then light that went through the left circular polarizer can make it through the right circular polarizer because it's been rotated. So that's what I've marked as medium force. Okay, and if you rotate it too far, you actually get black in the center again because once it rotates the polarization far enough, it can't go through. And so we have, and Bob Behringer pioneered this, and my lab uses this a lot, is quantified this so that we can actually measure vector contact forces at all of these points. And use this to very detail understand the particle scale interactions between grains. Okay, and so this is a really valuable tool that here on Earth we've used a lot to understand what's going on. Okay, and this is us doing it for the first time in low gravity. So this is me and 2 of my students on a NASA-funded experiment, and you can see that we're beginners and we lost contact with our experiment and had to be sent back. Okay, but in the end we were successful. Okay, so we performed experiments on Martian, lunar, and microgravity with these same photoelastic grains I just showed you, and these are the little prince experiments. We inserted a probe, a flexible probe, into this material and looked at how the behaviors changed as a function of the amount of gravity. And what you can see is that when there is gravity, there's sort of an underlying support structure, or rigidity, that comes from the forces between the particles, okay? And that the probe tends to get stuck on those forces and then has to jump to the left or right to get around them as it goes in. And that's not happening in microgravity. Okay, and you can see some effects of G-jitter here. Things are moving around. So in microgravity, you're not seeing that underlying state of force chains, and so the probe is able to slip in much more easily. So I'm going to show you movies of two of those. So Mars and microgravity for comparison. Okay, it'll start up in just a second. The motors will start to descend, and even without being quantitative, there are qualitative differences in the behavior. So on the left, the probe is getting stuck and finding its way around particles. And on the right, first of all, G-jitter, but also the probe just slides through without much resistance, very low forces. Okay. The advantage of the flexible probe here was that it's not actually popping grains off into the air where they would have escape velocity and leave. Okay. So we've quantified that, and here are some of the folks who were involved in that research. So the lead author on this was Jack Featherstone, who made a pandemic project of doing some more experiments on Earth and analyzing it. And what we see is that the Earth, lunar, and Martian data, if we just count how many stick-slip events are, they're all quite similar to each other. And the microgravity is very different. Okay, so there seems to be a step change between those, but of course we don't have any data points between them because that's not accessible on parabolic flights. Okay, it would be really nice to have things in between there. If we look at the net force, right, it's actually basically zero force for microgravity, so I didn't even put it on here, right? You can see that they sort of space out from each other in the order that you might expect. Okay, so as we do this, and as we learn how to do things in variable gravity, it opens up options for planetary science. And this is just sort of an inspirational photograph from the Mars HiRISE mission, showing that, the surface of our planets, geologists will recognize features here of, boulders tumbling down a hillside and things that, look like erosion channels, but, it's a question of what they've been caused by. Okay, and how do we go about doing planetary science in environments which we are primarily learning by images? We're visiting many fewer of them in person, and what can we learn? And how does knowing about granular materials help us do that? Right, and so if we want to do geomorphology on the moon or Mars, and this is a crater on the moon, I've shown a picture here. It's got failure planes that are reminiscent of stuff we see on Earth, right? We need to understand how gravity changes granular dynamics if we're going to make that comparison to the Earth, where we're much better at understanding how geological structures form. Like we just, we don't have that expertise to make that connection yet. Okay, we're building it up rapidly, but improved experiments would help with that. And then at the largest scales, in fact, the whole planetary system, the whole solar system, formed because of granular instability. I mean, it was dust. It was dust that coalesced. It coalesced heterogeneously. And I'm using Saturn as an example because it has a bunch of features, right? You have large bodies, you have smaller bodies, and you have stuff that never made it in the rings. And what allowed those to coalesce or not depends tremendously on the intergrain interactions, right? And in a very low gravity environment, what are they? Well, low gravity environment in the rings, right? Different amounts of gravity other places. So models of solar system formation depend on the kinds of experiments that we don't have. So what platforms exist for us doing more experiments, right? So I'm listing 4 here: drop towers, sounding rockets, enhanced gravity, and airtables. And then in the picture, I'm showing something that's on the International Space Station, which is a centrifuge that can give you larger gravity, actually. And I'm going to start by telling you about ground-based microgravity experiments, because that's actually what I mostly do. So I actually work in a zero gravity environment on Earth. The caveat is I have to work in 2 dimensions. So what you're seeing here is a picture of an airtable viewed from the top and forces within that system, and all of the particles are floating on a light, very gentle cushion of air. So they are in an equipotential gravitationally and are interacting with themselves and not with gravity, essentially. So we can do zero gravity experiments. We can't do them in 3 dimensions, we can do them in 2 dimensions. Okay, and Jonathan Kollner has been instrumental in developing techniques, starting from when he worked in his group and continuing now in Duisburg, of taking pictures like the ones you saw and reconstructing what the forces must have been to cause that picture. So I'm calling this image and pseudo image. And so we know the vector contact forces at all of one of these points, okay, which lets us essentially do really nice statistical mechanics, okay. And so this is some work that he did with Ephraim Billing and me a couple of years ago, where Ephraim did experiments on that table I just showed you and compared different kinds of stress. So biaxial, actually this is strain that we are applying and we are measuring stress, biaxial, uniaxial, and shear. And looked, in this particular case, this is just a sample type of result, that as you change the amount of free volume, which is on the left axis, and you look at the pressure, which is on the bottom axis, the statistical distributions that you observe are quite different in these three cases, right? And so we used this to understand how the history of loading affects, from a statistical mechanics perspective, what the microstates are, what the macrostates are, and if there are things like temperature that control transitions in behavior. And in order to do these experiments, we need to work in zero gravity because we want to probe things that the forces would change if gravity were there, right? And so the ability to do experiments in low gravity in 3 dimensions doesn't exist on Earth, but it does in 2 dimensions, and so that's where we work. Okay. If we want to talk about acoustic propagation, getting to low pressures is really, which requires zero gravity, is really important. And so in simulations, this is some plots that Zorana Zarovchik included in her PhD thesis, again, like 10, 15 years ago. She's able to compare a very statistical mechanics property, the density of states or density of vibrational modes, right, at low pressure and high pressure, and see that there's an increase in the density of states at low pressure and low frequency. So low frequency modes increase for very low pressure systems, and actually the patterns of vibration associated with those are quite different from each other. Okay, she can get to really, really low pressures inside a simulation because she just turns off gravity in the simulation. She never puts it in. Here's the equivalent experiments in our lab. Okay, and we are doing these in a vertical slit, so gravity is, pushing down, and so we have force chains there. And when we do an equivalent measurement, we do again see this increase in low frequency modes at lower pressure, but we're limited to how low in pressure we can go because we have gravity. Okay, and we cannot do this in 3 dimensions so easily. Okay, so again, for doing statistical physics of granular materials, access to low gravity systems is really important for us. Okay, and there are 3D zero gravity experiments, and here's where I'm jealous of my colleagues in Europe. So Kirsten Harth and Jonathan Colmer, these are some experiments that they have done, either on sounding rockets, and this is the Drop Your Thesis project that funded the one on the left. And so you can look at granular gases, and on the right, Jonathan, in much more recent work at the Bremen Drop Tower, can study things about the interactions between grains by dropping an entire apparatus for several seconds, right? And these are things that, again, like I said, I find my colleagues in Europe have much more access to and are able to be much more creative with. All right, so summarizing the stuff we've talked about. All right, so we need to safely explore. And by that, I mean 2 things, right? When we're going to visit someplace in space, one challenge is not to make a mess of wherever we visit, right? That we leave it so that future generations, can enjoy places that we haven't trashed because, we messed up visiting them, right? And, landing on an asteroid that has very, weak properties, is a place where that's a potential, for danger. And the second challenge is we don't, and maybe the order of these 2 should be reversed, probably should be, is we don't want to hurt the human or robot explorer, right? And so we need to be able to, at a minimum, understand granular dynamics well enough that we can achieve these 2 aims, right? And we are really at the limits of our knowledge being able to do that safely. There are also a ton of open questions. So all of the stuff about, in-situ resource utilization and, planetary geomorphology, they rely on us sort of being able to redo many of the things we've done on Earth to understand granular mechanics, and this can be granular segregation, so the Brazil nut effect, right, where the big nuts end up at the top of the pile, right? Granular gases matter for how we're going to handle launch sites, and landing sites, how well things are stable, right? If we're going to build permanent structures for power or living, like we need them to be stable and not degrade in ways that are dangerous. If we want to explore, we need to be able to do things like dig and anchor and locomote, and that involves sort of experiments on Dragon and Intruder, right? So everything on the left are things we've done in Earth gravity and we haven't done in other gravities and are therefore huge open questions. And these are some of the people and some references of people who've been thinking about a lot of these other issues. Okay. So I'm going to go back to go back at the end to what I started with in the beginning, which is, why NASA should be interested in physics research on granular materials. And, the first two here are that there's some really fun physics to be done. When you change temperature of materials, they change their properties, right? And that's sort of the classic materials science, condensed matter physics, approach to things is you turn some knob and you watch how things change. And so, changing gravity is a knob that we have not played with much, right? That as you tune that knob, what happens? What interesting, phenomena exist that we haven't seen before? And understanding that our models may not survive some of those new probes. As we change gravity, maybe our models don't work in lower gravity or in higher gravity, right? And so we're going to improve our ability to model these systems, by doing that. And so this is sort of where the physicist lives, is in these first two ones. And then, of course, the hope is that the things that we learn from doing physics, matter, in the broader scheme of things, right? And I think that they will lead us to be able to do better planetary science, right? And better and safer ways to explore the universe that is the source of so much wonder. Even laboratory scientists, want to be able to be a part of understanding those last two things, and that's very squarely where I sit. All right, thank you. I'm going to unshare so that I can see the videos again.
Thank you, Karen. I mean, this was really well put, I would say. Like, as we talked multiple times over our phone conversations, like I personally believe that granular media should be one of the main focus areas of our soft matter science, because there are so many interesting science and physics that are still unexplored. If I may ask, do you think, because this is based on my previous background of working for a for-profit organization, manufacturing company, is what I have found out, like most of the even improving life on Earth from that perspective, most of the materials start with granular material at one point of time. And in my experience, I have seen the biggest challenge that happens is people really don't understand how to handle massive amount of industrial scale material. And
Yes.
as a result of that, they end up using a lot of resources. I mean, I can tell you, like in private, like how much I have seen that resource being misused. So my gut tells me, like, having this better understanding will not only help improve our space exploration capability, but can actually help life on Earth, because that is directly related to reducing the energy demand, reducing greenhouse emission, and things like that. So it's a extremely hot topic of interest in my mind. What do you think about
I
that?
think that's absolutely true. I mean, so resource handling, I mean, I just said a large fraction of the industrial products that we handle in the US spend part of their supply chain as granular materials. So, polymer powders, seeds, coal, lots of things spend time there. And any time that those processes are disrupted, it's wasteful, right? And so people over-engineer because they need to be able to handle the extreme cases, and that costs money and resources. And so actually part of my lab has been involved in trying to understand how to improve, handling. What are the models that improve handling just here on Earth? It's funded by industrial companies, right? Because that's such a problem. And yeah, so I think that if we can do a better job at that, we save resources, and that benefits life on Earth too.
Okay. So I will start with one question I had, and then I will. So when you were showing that slide where you were poking in your that parabolic flight experiment, I saw like they were like basically capturing that probe in not microgravity, but in a reduced gravity condition. Whereas in microgravity, it just basically went through without Why is that happening?
So in fact, pulling the probe out is easy. We haven't done experiments on anchoring. So it's not captured yet. It's just that it's getting stuck and it's hard to push in. So this is an example of, and it's more like pushing a spade into your garden, right? That if you're pushing a spade in, the spade can't go in if the grains are in the way. The grains need to go somewhere, but there's other grains there, so they can't, right? So this is a geometric effect. But in microgravity, it's pushing in and there aren't strong forces between the grains and there's no gravitational energy cost to just moving them up. And so you can just move up and then you have more space to move around. And so being able, so pushing intruders in is fundamentally different than low and high gravity. And what I'm not showing here, and actually Troy just put something in the chat, is we've actually just started doing experiments where we in fact tilt our airtable. And we are looking at trying to go from, say, 0 gravity up to about lunar gravity, how that changes pushing an intruder in. And I did not present those results because they're a little bit too raw to show in public yet. But in fact, that's another place where we can do earthbound experiments and address things that matter for, exploration and safely understanding how to anchor or dig on surfaces.
Okay, awesome. So Leslie, I think you had a question. Do you want to ask a question?
Sure. I was just wondering how mature is our understanding of granular mechanics? So, and how well does it predict the behavior of soils here on Earth? Natural soils, not just the regolith, but there's also the effects of life. Because right now, soil engineering uses a lot of empirical rules of thumb and so forth, and I was just wondering what's your take on that? I know you've had some future work to do, and how well are we doing right now?
So we're doing, so we'll just take as examples that, civil engineers have been building buildings that mostly stay up for a very long time, right? Where they can't handle it is when there's erosion and earthquakes and things like that, that push things past the limits of stability, right? And so, but the way that they do that is by building things with many safety factors built in, right? So you don't want to engineer with granular materials. You want to stay far away from where the instability is and put in a large safety factor, right? Because things are so heterogeneous and, small perturbations can change things, right? So soil liquefaction is in earthquakes, like you had stable soil, but the sound waves going through it destabilize those contacts, right? And now you've liquefied your soil and buildings can actually sink, right? And again, we have civil engineering standards that address that, right? But we just saw, incredible loss of life in Turkey. That there's, that would have been, if there were good engineering standards that were consistently put into practice, in, Earth seismologically active zones, there's a huge, possibility for saving a lot of lives, right? And it's not that civil engineers don't do this; they absolutely do this, right? It's just really, really hard, right? Yeah, so more, and it's actually the theory that they're using for soil stability is called Moore Coulomb analysis. It's the same Coulomb that we know from Coulomb friction, right? This is an old and functional, very functional branch of engineering that also has to build in large safety factors.
But
Yeah, that's what saved us is large safety factors. Yes.
Yeah, and then if you're going to fly materials into space and you have to pay for extra because you have to build in a large safety factor, that's not so good for planning how you use your resources in space, right?
No,
So
thank you.
Karen, if I am hearing this correct also, so as you mentioned during your presentation, that the laws of whatever, like the type semi-empirical laws that we use, they don't scale well.
We don't know if they scale well. No one's done this.
Okay, so we don't know. So okay, so there is a possibility this may or they may not scale well.
It's an open, yeah. So like if I build a structure on the moon that was built to Earth standards, right? What safety, I don't even know how to start to estimate that safety factor. And I am not a civil engineer, so I don't know how to do it on Earth either. Let's be very clear, right? But I wouldn't know what to recommend, right? because, you know, if we just do, you know, like, you know, the freshman physics, calculate the coefficient of, you know, friction, you know, the internal angle of friction, gravity drops out of that equation, right? And yet we know, right, that things are different when you have other effects. So our probe could go in much more easily, right? So like, it's not the same when you have different amounts of friction, even though some really, you know, sort of classic analyses suggest that you might not need to worry about gravity. You do need to worry about gravity, and sort of freshly redo a lot of the classic civil engineering results need to get redone, right? And that's just a fact. They need to get redone under other circumstances.
Absolutely. I think, Padita, you had your hand up earlier. Are you there?
Yes, while Karen was showing the birefringence method, the samples that she put it in this kind of like a disk, the sample itself, are they real granular or are they spheres or disk?
So they're real. They're made of real materials.
Okay, so
that have real effects from roughness.
I mean,
right. But I want to be clear because this actually matters, right? So we know that if we change humidity, if we change roughness, right, all of these things influence them because they are real, right? What they are not is angular, right? And I have not done experiments on angular particles, but other people have. I have done some experiments, not many.
Okay. So real mean they are not transparent.
They are transparent, because that's what let the optical technique work.
So do you think that is it the light that goes through those materials? If they have the original birefringence, will it matter your experiment? Because see, the material itself is birefringent in nature. Because you're measuring them by birefringence. I'm not telling you that you're doing it wrong, okay? But I'm trying to factor in if there is a what your intrinsic birefringence of the transparent material would contribute the stress or the stuff that you are looking into.
Yeah, it's a non-invasive method. So the light is not introducing additional stresses. What it does is it sets that you can't use any material you want. I mean, glass is also birefringent, quartz is birefringent. There are a lot of birefringent materials out there, right? But all of them have the shared property that they simply rotate the polarization of light that goes through them, and that's a very non-invasive effect.
So
the light is not influencing the experiment. The light is merely the means by which we read information out of the experiment.
I mean, light interaction to these particles, it's through the birefringence that you're measuring. But I was under the impression that you're measuring the birefringence property of the material itself or the entire ensemble itself.
So I am doing it, so depending on the experiment, lots of, okay, but in our most precise, most physicsy experiments, for every single particle in every frame of the movie, we measure the normal and tangential forces at all of the contacts. And so then we can coarse grain that into things like stress fields and calculate, doing a full stress tensor analysis where we separate pressure from shear components, just as an engineer would do it, right? So it depends on what we're asking, whether we do the full detailed every single contact analysis or if we zoom out a little bit and don't.
Oh, okay. Yeah. Well, I have more detailed technical question, but this is out of the regime now. I have to let other people discuss on different matters related to this too. Okay, thank you.
So Sharmila, you had a question. Do you want to talk about that?
Yes, sure. So thank you, Karen, for an excellent talk. Just fascinating. Love the videos, love the data. So I wanted to go back to what you had begun to explain because I had a similar question. The regolith has such a unique set of properties, right? It's angular, it's it's a mixture of glass and other materials inside, how it's created, a lot of static, clings to materials. So how do you think that would compare to the colloids that you're using, and what kinds of adjustments do you think one would have to make to kind of model those properties?
Okay, so first of all, I want to say that my particles are not colloids; they're centimeter size. They're actually much,
Okay.
they're much bigger.
Okay.
They're much bigger than regoliths. So for starters, size is a big difference in addition to everything else. So in fact, in our parabolic flights, we did experiments both on simulated regolith and on the photoelastic grains. I only showed you movies of the photoelastic grains. Okay, so I will say that our experiments on the regolith suffered some technical difficulties, so the data was not as good as the data we got from the photoelastic grains. But in fact, we saw some features that were very, very similar. So this issue of it being easy or hard to push in, 100% that happened in the regolith as well.
Okay.
The data was only semi-quantitative, and it's in the paper actually. So we did publish that. It exists, and it's a real phenomenon that happens even with real grains. Yeah.
Got it.
The disadvantage there is that we can't see the forces. We can't measure forces so easily, right? And so that's the advantage of the fake materials, right? And they're real materials that are fake properties, right? Is that they let us see things that the real regolith or the simulated real regolith doesn't.
Yes. Yeah. Yes, exactly. And just FYI, even with regolith simulant, what I'm learning now, because we put out a solicitation for regolith very recently, and so I've been working with the Apollo regolith folks for a little bit now. So there's also I'm sure you know this, there's also a significant difference in terms of,
and thankfully through our UCF collaborators, through Eddie and Josh, we had access to the simulated regolith, which was already for me a huge advance. I can't even imagine being lucky enough to work with real regolith.
Which, by the way, you can apply to the Aries. They have a process, and twice a year or something they look at proposals and assess it. There's criteria, but you can go to the website and check it out. So there are ways you can actually ask NASA for real regolith as well.
Yeah, that's good. Yeah.
So thank you again.
Yeah, thank you for that.
I think Henry has a question.
Hey, this is super cool. Totally fascinating experiments that you're doing here. So I thought this 2D air table that you mentioned was really interesting because it's pretty similar to a lot of studies that we do with like dense planetary rings, like the really big rings of Saturn. And in these rings, you have a lot of collisions between particles. And actually, a lot of the numerical simulations are 2D, just like your air table too. Yeah. But there's one thing that we have in the rings that you don't have in like your air table, which is gravity between the particles, not gravity overall, not like a surface gravity, but gravity between the particles. So do you have some way of, an analog by which you can simulate gravity between particles with electrostatics or anything like that?
Yeah, so people have put magnets in them. Yeah. So people have done stuff. Yeah, so you have to be careful because, I mean, you like you say, you can play with electrostatics, play with magnets. You won't get gravity because it'll have a different functional form, but you can get interparticle interactions. And unfortunately, of course, with magnets, they're dipoles, and there's no way around that. But you can get them, and people who work with those either electric or magnetic interactions can get clustering to happen, right? I actually think that cohesion is actually not terrible for that, because you want things to stick together, right? If they get close enough. And actually some colloidal studies where that's possible by tuning, Debye, layers and things like that. I think there's some stuff that can be done in wet environments that are analogous in ways that the dry granular case, it can't be analogous, right? But then there's drag from the fluid, right? So you can't sort of piece together all of these things in one place. I think it's going to be a lot of experimentalists, working in different quadrants and putting in one force and not having another, right? Until you sort of piece together enough knowledge that you've seen the whole elephant, right?
Thank you.
Okay, if there is a question, I mean, you can please go ahead and ask, unmute yourself.
And Troy just mentioned in the chat that acoustically levitating particles is another way to get, besides airtables, another way to get them out of the gravity and into the same plane, right? And then you at least can work with spheres, or you could acoustically levitate regolith. Like that gives a lot of opportunities that an airtable cannot give. It also is much more constrained in sort of the size of system that you can work with, and I can work with much larger systems. So many of these platforms that we're talking about, like they don't work for some things and they do work for other things. And, I think a whole suite of Earth-based experiments are possible, right, where you target different questions to appropriate platforms.
So Karen, I would like to ask one question, which is you were mentioning about the impact of the van der Waals force. Okay.
Mm-hmm.
So can you elaborate on that a little bit more?
So for those who don't know, van der Waals force is like what lets geckos run up walls, right? So it's the dipole interactions essentially. They're basically intermolecular forces, and there's enough of them on the foot of a gecko that it can stick to a wall, right? And so we don't think of these as being strong forces in general, right? But in fact, the asteroids, right, the gravity is so weak on them that the molecular forces between the surfaces, right, due to these van der Waals forces, are large enough to actually stabilize something under rotation, right, that it doesn't break apart, right? Where if it were only the centripetal effects with gravity, it should break apart. It doesn't, so there must be some adhesive force, and the forces, and this is the work of Paul Sanchez in particular, right, say that those forces are large enough to stabilize that. But it's incredibly difficult. If I want to talk about sticking forces between very small objects with very small forces, those are extremely careful physics experiments that have to get done, right, to measure those adhesion forces. And there's a lot that could be done there to understand what the van der Waals forces are in those cases. And then you have to ask the question, does the vacuum of space matter? Right, there are these asphaltene molecules, right? Do they have a vapor pressure where they come off or not? Right, there's a huge array of surface science questions to be asked there, on which I am not an expert, right? I just know that that's a huge mess.
Okay, I think Padita has his hand up.
Yeah, discussing about van der Waals interaction. Correct me if I'm wrong. I'm not in this field of physics, but if I understand it, when I was listening to Jaeger's talk last year at ABS, isn't it that this van der Waals interaction is the primary one that started the dust that comes together and makes into asteroids, right?
So that is in fact what people are there is some consensus, I think, beginning to coalesce around that. And you have to, you don't get anything stable unless stuff sticks together, right? And pretty much the only force you've got, to work with is van der Waals, right? And so I don't want to say that that's absolutely it, but that does seem to be developing as something that seems likely to be true. But we don't have tons of data. Right, it totally makes sense.
Okay.
And we don't have tons of data. Those are both true.
Okay, they were trying to do by levitation with a very strong ultrasound levitation.
Yeah, exactly. And this is what Troy was mentioning. There's some good comments in the chat about that in fact you can get effective interactions that look gravity-like, right? And I think those are really promising experiments to look at, when electrostatics versus van der Waals is dominant, right? Because you can change material properties. So as a soft matter scientist, I can pick my spheres to be of things that I either know are hygroscopic or not, that are surface coated or not, right? And then look whether things stick or not, right? And so there's a lot of space to do that and sort of tease apart, a nice little, parameter space diagram to figure out which effects dominate in which cases. And I think those are great experiments to be done.
I see, right. Except that on ground, that levitation is you cannot, well, of course, you cannot lift the entire asteroid, but they were trying to do with the very
dust.
small particles that they can levitate it, and then they were trying to spin it Yeah.
And spinning it,
Spin.
and they actually were able to spin things in their acoustic
Right,
levitator.
and spin
Right.
and see how they come together. Is that
Yep.
due to the electrostatic or the van der
Yep,
Waals that is
exactly.
overriding or competing? Yeah,
Mhm.
they were doing that. That's a
Yeah.
very interesting.
And there's another, as an experimentalist, there's another really big, there's a couple of really big advantages to ground-based experiments. So one is that, I mean, I told you that my experiments in the regolith didn't work terribly. They didn't work as well as we wanted. Once you're on the parabolic flight, or once things are in a sounding rocket, or once things are on the ISS, there's not much you can do as an experimentalist to twiddle things to get it back to working again. Right. When you have a ground-based experiment, and drop towers, give a lot of these capabilities as well, you can play with things until they work, which is, as experimentalists, what we often have to spend a lot of time doing is finding the parameter space that actually, where you can do experiments. And so there's an efficiency that goes beyond cost and greenhouse gas emissions and all of those things, right? I mean, anything that's off the Earth's surface is expensive, in many, many ways, right? Things that are on the Earth can be very, very accessible in ways that improve the science, right? They're not only cheaper, you can do really good science that way because it's a human interacting with it and, being a human making good human decisions.
So in your mind then, Karen, you think like having for granular media research, like access to proper like a drop tower with various level of gravity and a longer duration, not just 2 seconds and longer duration. That's why you were mentioning about University of Bremen's can actually help a lot of these which are otherwise really, really expensive, takes years of preparation to do, and often does not give out as important result as you might wish it to have.
Yeah, I mean, so you have the ability to repeat the experiment, right? Without great.
And within 5 seconds or 10 seconds.
Right, like that didn't do what I was supposed to do. And a lot of the skills of an experimentalist are figuring out what the right experiment to do is, and you only often figure that out by playing, right? And so I think that the closer the experiment is to the laboratory, right, the easier it is for that element of discovery and play to be contributing to good science.
Absolutely. Is there any question from the audience anymore? Yes, so try. You wanted to say something? You don't have. You can unmute yourself if you would like.
No, I just wanted to second what Karen was referring to, that not all experiments have to be sent up on a rocket into a space station. We can do a lot on Earth, and it's more climate friendly. We should be aware of that.
Yeah. It's also undergraduate researcher friendly, right? So like, where do our scientists come from? Well, they were kids who liked NASA as kids, right? And let's be clear, NASA has a strong band. I own a NASA t-shirt. I don't own an NSF t-shirt, right? Right. Those kids become college students who want to work on things that are relevant to NASA and space. And if it's on an Earthbound system, they can work on it and be contributing to NASA's mission in a very, very accessible way that doesn't have the same barriers, right? And, my parabolic flight experiments were successful precisely because I had more undergraduates excited about participating in that than I could actually take onto the project. And they worked so hard to make it happen. And then went on to professional careers, some of which are in space-related things, some of which aren't. But I think 3 of the 4 are doing space-related things. And so that expertise is going into the space program, right? Because they had that laboratory experience as undergraduates. And, okay, parabolic flights are somewhere between ground-based and Earth-based, but the point is ground-based stuff would let even more students have that, really important professional development experience.
Absolutely. And I think you were talking about undergrad. We have an undergrad intern, Carolina. So Carolina, are you there? You had your hands raised.
Oh, yeah, I did. I had a question about one of the earlier slides where you said that you put stress onto a material and then it was able to, like, waves were able to go through it, whereas before the stress, they weren't able to. I'm just curious with the stress, does that mean, like, did you just add pressure to them?
Yep. So stress is
Okay.
just a fancy name for pressure.
Okay.
Or squish. I squished them, right?
Okay. Okay. Gotcha. Okay. So
Yeah.
just by
Yeah.
pressing them
And actually, it's not that
together.
and it's not that it can't go through in one case and it can in the other. It's not a gating situation. It's that the way the light is transmitted, we can detect on the other side of the particle, right? And this is this non-invasive technique. Yeah, and I mean, if anyone hasn't seen this, get a plastic fork and get 2 pairs of polarized sunglasses, crisscross them, put the plastic fork between them, and play with pushing on the plastic fork, and you will be able to see this phenomenon. Right? It's nothing exotic. Right? It is.
Okay.
It's
All
nothing.
right. Thank you.
Yeah.
And actually, I would just like to add, like glass blowers have been using this for centuries.
Yeah.
So if you go to a glass blower shop, you will see that birefringence or like photoelastic, the other fancy way of calling it. So
yeah. So this seems like a trick if you've never seen it before, but it is very old-fashioned technology.
Okay.
But if you've never seen it, it's going to seem like magic. I agree. But yeah, it's like good 19th century science.
exactly. So Padita, is that a remnant hand or you had a new hand raised up?
Sorry. Yeah. No, I'm done. Thanks.
Okay, okay. So is there any more question from the audience? Okay, so if not, so I would like to thank Karen. Really, thanks a lot. You communicated extremely, extremely well. I could not have done it better than what you have done. And just for the audience, we will have this seminar series moving forward. I'll just bring back the slide just for, let me share my screen. So we have our next seminar, which is a high-speed optical imaging method for soft matter science. We are Dr. Lawrence Wilson from York University and Joe Bradley from University of Edinburgh. They are going to talk about 2 very interesting methods. These are called differential dynamic microscopy and digital holographic microscopy. If you have not learned about this method before, I would strongly, strongly suggest please attend this. Ask your students also to attend because this is really fascinating technique. We were introduced to this by these 2 gentlemen, and they have been they helped us a lot through this process. And I think it will be a great opportunity for others to learn about this. So without much further ado, I would like to say thank you, Karen, and thank you everyone for attending this. And look for another meeting invitation. We will have this at a cadence of 3 to 4 weeks. We're not fixing on a fixed date and time. But it will be happening at around like noon time, Eastern Standard Time. So, John, do you have anything else to add, John or Kelly?
Just thank you, Suman, for setting this up, and thank you again, Karen, for presenting very well, as many of the chat comments said.
And people ask really good questions that are hard.
Thanks, Suman. I don't have anything else either. Thank you, Karen. Appreciate your talk today.
Thank you. Okay. Thanks a lot. And see you guys on April 3rd.
Thanks. Bye.